Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is ET 122, Digital 2. Today we're going to discuss the parallel in serial out shift registers. But before we do that, I have a correction issue regarding the 74146, which we discussed earlier, which we remember right was a serial in parallel out shift register. And this is also giving us an excellent opportunity to practice reading our ANSI-IEEE dependency notations. Okay, so this is some mysterious looking blocks, and this is 74164. If we remember, was, serial in, parallel out. So what I said, which was mistaken, and you can easily see what the mistake is. I said there's one data input, the serial in, but its actuality is two data inputs, A, B, and I said it was a NAND. Well, just looking at this diagram, is that correct? Provides my data input? Well, no, because check it out. It's an AND. Sorry about that, guys. So while we're here, let's actually discuss this. Anyways, so what is our qualifying symbol? Shift register 8-bit. What's this notched block up top there? That's the control block, and that has common inputs. Looks like there's only two common inputs, our clear and our clock. Of the clear and the clock, which one's the control element? Obviously, that guy. Clock is the control element, and it's the number after that, that's 1. So it's controlling everything with a 1. So sticking strictly with the control block, is our clear synchronous or asynchronous? Well, because there is no 1 on this thing right here, it is an asynchronous clear, i.e. the clock is not controlling the clear. And how those things are set is just an R for a reset. So what is controlled by the clock? Now let's go down to the individual elements right here. So the individual elements, the thing the clock is controlling is 1D. So A and B basically make our one data input, D, and it's controlled by the clock. And which way is it moving? It's moving from Q0 to Q1 to Q2 to Q7 because it's shifting that data right. Okay, so I think that's all I wanted to talk about, the 74164. Again, sorry about that, guys. It's not an AND, it's an AND. Okay, so what are we talking about? We're talking about parallel in serial out shift registers. Again, using our analogy of the bus, it's a simultaneous load. Everybody's getting off the sidewalk, clambering in through the windows, the exit door, every single door available. But when the bus is on fire, you're getting off in single file. You wouldn't want to do that if it was a real bus. But we're talking about registers. So parallel in, everybody's coming in simultaneously. Serial out, everybody's getting off in a single line. So how do we do that? Obviously, we don't want things just, one of these guys going in, this one's going in, this one's not loading, this one's not loading, and then that loading. You want everybody to come in together. So there's got to be a command, maybe something like load, like an active low load. There's got to be a command, okay, everybody get in now. And there's also got to be a command to everybody get out now. And that's often takes the form of shift. So everybody load, everybody shift one right, 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 everybody's off the bus. Okay, so let's go into the logic diagrams to make that work, logic circuits to make that work, and I might as well do a timing diagram. Okay, so here's our 4D flip-flops in close proximity. So what's its capacity? Obviously 4 bits. If it was straight up serial in, serial out, just think in general terms right now. Well, first off, before we do that, we got to give it a clock. Everybody's got to have the same clock. Can't go anywhere without that. Okay, so serial out. So obviously serial out, one flip-flop. Just think in general terms right now. Let's not even draw any gates or anything like that. So one flip-flop has got to give the next flip-flop what it's on its output. So that would mean, I'm going to draw this in a different color because these are just general things right now. This one has got to pass it to this one. And that one's passed it to this one. And that one's passed to this one. And it comes out that way. Okay, so it's almost like a bucket brigade. Two hands it's stated a 3. One hands it's stated a 2. 0 hands it's stated a 1. That means 3's off the bus. Then 1 to 2, 2 to 3, and so on and so forth. So that's serial out. But now parallel in. So parallel in implies that, I'm going to get rid of our discussion about serial out. Parallel in implies that data is coming in that way. Data is coming in that way. Data is coming in that way. And that way. So that's not as complicated as previously. But what we got to do is we've got to make a command. Okay. Is everybody waiting to get on the bus? Is everybody there? So once everybody's there, let's load it. Okay. So how you can do that is give everybody an AND gate. And that's where its data is. And when you want to load them, give them a load command. So when load is high in this particular case, and this happens to be a 1, 0, 1, 0 here, what's the output of those AND gates? 1, 0, 1, 0. But if load is 0, I mean you don't load it right now. Remember, anything ANDed with 0 is a 0. You're not loading anything. Okay? But just to make matters slightly more confusing, we want an active low load. So let's invert that signal right there. Okay, so now when load is a 0, it's a 1 there. And 1, 0, 1, 0 gets loaded in. Okay? Not too difficult there. But now we've got to go ahead and combine that whole functionality of parallel in with our previous discussion of serial out. So we've got to come up with a situation where we can either have parallel in or serial out. And the key word I put there is obviously an or. So what we've got to do is definitely put an OR gate. But we've already come up with we've already did the logic diagram for our parallel in. But now we've just got to OR it with our serial out. And that is a shift command. And shift, just to be thrifty, is actually the opposite of load. So we only really need one of those. So it's not like there's a separate shift command and a separate load command. If we want it to shift, i.e. to read, So, excuse me, take data out, we give it a 1. If we want to put data in, we give it a 0. And we'll go ahead and show you how that works by putting our shift, i.e. enabling our serial data out with this combination of parallel in. So what I've done here in this diagram is I've redrawn our load with our ands there, and now I've done portion of the shift and I've done that in red. Our parallel data, I've done that in green. Okay, so let's describe this here in further detail, and we'll expand upon the shift, i.e. the serial out. Okay, so like I said, we've only got one command, shift and active low load. So what's the red? That's shift. Okay, in shift, we want to pass the previous stage's Q to the next stage's D. And we do that with these ands, ors. Okay, so think from the perspective of shift. So when shift is 1, this AND gate, what's it going to do? Well, it's going to pass the previous stage's Q to the next stage's D. And basically it's going to go like this, in through here, through there. Basically, we've made a serial out. We're passing the previous stage's Q to the next stage's D. So let's go ahead and continue this here. Okay, so what I've done here is basically I've done all of the serial out stuff in red and all of the parallel in blue. So let's visit again step by step here. So we're given this load line a 0, which makes this a 1, which, what was our number before? I can't even remember what it was. I'm just going to say 0, 1, 0, 1, 0, 1. All right, so when that load line is 1, what's going to get passed to here? A 0, a 1 here, a 0 there, and a 1 there. But now think about what's happening when load is 0. What is shift? That's also a 0. So these AND gates here, that's getting a 0, that's getting a 0, that's getting a 0. Placing a 0 there, and a 0 there, and a 0 there. So from the perspective of this OR, 1 OR 0, a 1. 0 0, a 0, 1 OR 0, a 1. We've already done this analysis, that's a 0. So what have we done? We've loaded 0, 1, 1, 0, 0, 1, 1. Ta-da! Clock pulse comes along, bang. That is what our Q inputs are. Excuse me, our Q outputs are. 0, 1, 0, 1. Now, we want to go ahead and shift. And how many, in this particular case, how many clock pulses is it going to take to get the data off? Well, there's 4 bits, so it's going to take 4 clock pulses to get the data off. Let's go ahead and clean this diagram up, and we'll go ahead and see how that's done. Okay, so I went ahead and cleaned up the diagram here, and now we're going to show you, well, previously what happened here is we parallel end 0, 1, 0, 1, and that I just showed you how we got 0, 1, 0, 1 on the outputs of the individual stage, respectively 0, 1, 2, and 3 of our flip-flops. So that was fine for load, and now we want to shift. So using our ingenious single command load shift, that changes to 1. So what's happening on this blue bus here? That's a 0 all the way across. So this AND gate here is a 0. That's a 0. That's a 0. That's a 0. So regardless of what's going on there, those AND gates are always going to produce a 0. But now it's our shift. Our shift command is basically enabled a path from the previous stage output to the next stage's input. Okay? Because there's a 1 here. And in this particular case, we've got a 0 there. And it's a 0. So 0 or 0 is a 0. We basically passed this 0 on to the next stage, 0. Same thing here. We've got a 1 and a 1. That's a 1, 1 or 0. So 1. We've passed that 1 on to the next stage. And now 0 and 1 is a 0. 0 or 0 is a 0. We've passed that previous stage's output onto the input. Next clock pulse comes along. The previous stage's input is loaded into the next stage. And basically what's happening, we were at 0, 1, 0, 1, 0, 1. Next clock pulse comes along. We've shifted it, passed it on, passed this guy on, passed this guy on. And there's somebody over here that's reading on the output. So just read a 1. Then it's going to, I don't know what happened there. Pass that 0 to there, pass that 1 onto there, pass that 0 onto there, and finally that 0 is kicked out at the very end. Ultimately, how fast did it take to load? Well, it's parallel in 1 clock pulse. How fast did it take to read? Well, it's 4 bits coming out in a serial fashion, 4 clock pulses. Okay, super fast load, slower download. Okay, let's talk about one device in particular, the 74165. That's an 8-bit parallel input serial output shift register. And additionally, it can also act as a serial in, serial out shift register. Okay? So that's a parallel in and a serial in. Serial out shift register. And that's 8 bits. And ultimately, what that guy looks like that's your ins. It's a serial out. So there's only one out. It's got that shift, active low load. It's got our clock. It's got this special thing called a clock inhibit. So if you basically want it to ignore the clock, just put a high on that clock inhibit for the brief moment you want to go ahead and ignore it. That means, okay, shift, shift, okay, stop. Everybody stay where they are. Okay, shift, shift, shift. Basically, that's what a clock inhibit is doing. And then finally, what's dangling off here? SER, like I said before, you can also use it as a serial in too. So 74165 is both a parallel in and a serial in, but it's only a serial out. 8-bit shift register. Shift register, 8 bits. Okay, let's talk about our last combo is the parallel in, parallel out shift register.